Kia ora koutou, no mai haere mai. Welcome to lesson 8 of introductory physics. This lesson is going to look at Newton's 3 laws of motion. In the previous lesson we talked about forces. We saw that forces are pushes or pulls that cause acceleration in objects, and forces are vectors. We talked a bit hypothetically about taking an object with no forces and watching what happens. It just stays there, versus if we start to apply a force, then it'll accelerate, it'll change velocity. Or if we've got two forces, then they'll sort of cancel out if they're equal, and the object won't move as if it had no forces. So we've already met a bunch of the ideas that are contained within Newton's laws. What we're going to do in this lesson is take all of those ideas and wrap them up formally into Newton's 3 laws. So that is all we have to do during this lesson, just learn the 3 laws. As usual, there'll be a few extra bits and pieces we add in along the way, including, to start with, looking at mass and inertia. To get an idea of where this stuff came from, where Newton's laws sort of came from, it's a good idea to look back at what people used to think before they started to really understand the physics of even just everyday scenarios. So Aristotle, ages ago, thought about the motion of things, and his philosophy was that everything had its proper place. For stones, that was resting on the ground or at the bottom of a lake, so underneath everything, right at the bottom. And for smoke, it was right up at the top, above everything, above even the air. And the speed of the motion of something going up or down depended on the density or the weight of the object. The heavier ones go down quicker and they get down right down to the bottom. The lighter ones that are less dense than air would go up really quickly and get right to the top. And there's some aspects of that that are valid, but in general that's not quite true, as we'll see. Sideways motion for Aristotle was only created by pushing or pulling something. When you stopped pushing or pulling, sideways motion stopped. Things cared about where they were vertically, and they would always try and get down to the bottom or up to the top, depending on their proper place, but they'd only move sideways when they were pushed or pulled. You can forget all of that. It's just a nice little historical bit of context. Galileo Galilei came along and overturned a bunch of Aristotle's ideas. He determined 2 main facts, and they were that the motion of 2 objects released, then falling to the ground, will be identical in the absence of air resistance. Now, air resistance is very difficult to get rid of completely. There are videos, if you go on YouTube or various places online, there are videos of dropping things in pure vacuums. I think Brian Cox, if you're familiar with his work, he does a video where they make a complete vacuum and then they drop a bowling ball and a feather in this vacuum and they fall at the exact same rate. So you can see that happening. But obviously that's more difficult to achieve than Galileo would have been able to accomplish. Instead, what you can do is you can get 2 different objects with the exact same size but different masses, and that way their air resistance would be identical. Even though they still experience it, it's identical, and you can sort of ignore it as a differing factor. So you can have a hollow ball and a solid ball that are both the same shape and made of the same material would experience the same air resistance. The other thing Galileo realized is that a moving object which experiences no friction does not need any external force to keep it moving. So whereas Aristotle thought that something is only moving sideways when you push it, Galileo said, well, no, if you push something and there's no friction, nothing to force it to slow down, it'll just keep going. And so we see that again with a nice smooth ice surface. You push something on it, it'll slide for a lot longer than if you put something in a pile of sand and try and push it, it'll stop as soon as you let it go. From Galileo, from those concepts that he came up with, we have 2 specific terms. One we've already met, and that is force. He came up with the term force, meaning a push or a pull. The other one he came up with was something called inertia, and that's some property of matter to resist changes in velocity. It depends at least in part on the amount of material making up the object, which is what we call the mass. So this inertia idea is something to do with mass. The idea is that something with more inertia needs more force to get it going than something with less inertia. And for visualization purposes, just imagine a nice simple ball. If you put a ball at the top of the slope at rest and let it go, it'll start rolling down the slope. It'll accelerate. Velocity will increase over time. If the ball is already rolling and then it starts to go up a slope, then it will slow down. Right? It will slow down. It will have negative acceleration or deceleration. Whereas a ball on a horizontal surface, you can imagine that will just keep going. Right? If you remove friction, you start a ball rolling, it will just keep rolling forever. And that was Galileo's sort of his leap in understanding from what Aristotle had. Aristotle would have said as soon as you stop pushing the ball, it's going to stop. Galileo said it's only going to stop if something is actually pushing the ball in the other way. And that's where friction comes into it. So inertia is whatever it is about an object that resists changes in velocity. So I said in the previous lesson that velocity doesn't spontaneously change. And that's because objects have inertia. Inertia is something about the object that resists a change in velocity. As I already said, Galileo came up with this idea of friction, that something is forcing the ball to slow down. We'll talk more about friction in the next lesson. So Newton's first law is basically taking this idea of Galileo's and formalizing it as saying that if there is no net force on an object, then the object cannot accelerate. It will not accelerate. The no net force is slightly different than our hypothetical scenario where we said there were no forces. We're talking now about any scenario in which there's no net force. So there may be no forces at all, or there may be a bunch of forces, but they all cancel out so that there's no net force. And that's all Newton's first law of motion is. An object at rest or in motion at a constant velocity remains at rest or in motion at a constant velocity unless acted on by a net external force. Remember that the frame of reference we choose is up to us. So being at rest or at motion at a constant velocity is actually the same thing for different frames of reference. The main point here is that the acceleration can't change, there can't be an acceleration rather. There can't be an acceleration if we have no net force. And this is always true. As I said, if there is constant velocity, the net force has to be zero. It doesn't matter if it's some lonely thing out in space with absolutely no forces on it at all, or something in actually a really complex scenario with heaps of forces like a plane up in the sky flying along, or even possibly a boat in a storm at a specific moment might have a constant velocity and not be accelerating, or a pen sitting on your desk has a whole bunch of forces on it, but it's still got no change in velocity. I've already mentioned this part as well. The frame of reference, we can choose any of them as long as they're not accelerating. Our frame of reference can't accelerate. It has to be a constant velocity frame of reference. And that means that the velocity of the object we choose, we can just set it to whatever we want in our frame of reference. So that means that we can have moving objects that still have no net force on them. So we've got a moving object with no net force. Imagine a perfect sphere rolling along, excuse me, a perfectly smooth plane of ice in a vacuum. So we've got no friction, we've got no air resistance because it's in a vacuum, and it's just moving, rolling along this perfectly flat surface, perfectly horizontal surface. And the sphere is a perfect sphere, so there's no friction, no problems at all, nothing to slow it down. If the ball's already moving, then all we need to do is keep out of its way. If there are no net forces applied to it, then it will just keep rolling forever. In reality, of course, that's never going to happen. We can't make perfect vacuums. We can't make perfectly frictionless surfaces. We can't make perfect spheres. So there's a whole lot of problems with that idea. Theoretically, it's great, and hopefully it helps us understand what we're talking about with Newton's laws, but we can't realistically achieve that. We could, out in space, quite easily go and achieve that once we get out in space. But on Earth, we can't realistically get to a point where there's no friction at all and we keep moving forever. But suppose we've got a very realistic scenario. We're trying to move a large box across a floor. If we apply a force to the box, we can overcome that friction. So there will be friction. We all are familiar with friction from everyday life. It's whatever's resisting that velocity, resisting that movement. So friction will be pushing against you while you're pushing the box in whatever direction you want to move it. And if you make your push force exactly equal in magnitude to the friction force the box is experiencing, then you can reach equilibrium. You can have no net force at all because your push force and the friction force cancel out, and meanwhile the weight force and the normal force, the force stopping the object from going into the floor, are cancelling out. And so that will look something like this. We have four forces. The weight force, the normal force, which cancels out that weight force, the friction force, and the push force, which cancels out that friction force. So the net force on this box is 0, but it is still moving. You are pushing it along the floor. The fact that it's moving causes the friction force, and that's what requires your constant push force in order to counteract that friction force. So that's Newton's first law. Newton's second law is essentially very similar. In Newton's first law, we said if there's no net force, there's no acceleration. Newton's second law says, so if there is a net force, then there must be an acceleration. That's all Newton's second law is. But it clarifies that a little more by saying that the mass, do I mention mass here? Or maybe that's on the next slide. The force is proportional to the acceleration the object experiences. So a bigger force, a bigger acceleration. We already talked about that with our hypothetical object. So if you apply more force, you get more acceleration. But of course, we said that there is inertia, the mass of the object. We also talked about this hypothetically. The more mass you have, the more force you're going to need to get that acceleration to occur. So we've got these two ideas. Bigger force means bigger acceleration, but bigger mass means less acceleration. And that ends up being what Newton's second law is. The acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. So that's quite a mouthful, but most of you will probably have already heard Newton's second law in equation form. And that is acceleration is equal to net force over mass, or A equals F over M, or in the more common expression, F equals ma. So F equals ma is Newton's second law in equation form. It's telling us that the acceleration is proportional to the net force and inversely proportional to the mass. So you can see that from the equation, because if F gets bigger while M stays the same, in order for that equation to be true, A must get bigger. Whereas if F stays the same, the force stays the same, then if the mass gets smaller, the acceleration must get bigger. Or if mass gets bigger, acceleration must get smaller. So that equation wraps up all of Newton's second law into that one simple formula. The thing to remember, though, is that Newton's second law is always about the net force, but you'll notice I haven't written F net. That's because most of the time when you see this formula, the force is written just as F, not as F net. But please do remember that Newton's second law is always talking about the net force on an object. So it's the net force is going to determine the acceleration of the object. And so what happens in a couple of quick scenarios? Imagine that you've got a force on an object. What happens to the acceleration if you double that force? What happens to the acceleration if you halve the mass? And if you observe that the acceleration has been tripled, what happened to the force? So just three quick little questions. They're all fairly basic, no actual numbers or anything. They're all conceptual, but just to reinforce that relationship that we see in Newton's second law. So do have a quick go at this, pause the video, try and come up with your answers, and then on the next slide, I will show you the answers. So assuming you've done that, here are the solutions. A equals F over M. So if we double F, then A is also doubled. This is assuming the mass hasn't changed. If we double F, then A has doubled as well. But M is on the bottom. A is equal to F over M. So if we halve M, we've actually doubled the size of F over M. If you halve the thing on the bottom, you've doubled the actual size of your fraction. So in this case, you also double A. So you double A if you either double the force or if you halve the mass. For the part C, if we have tripled the acceleration, then you must have tripled the force. Assuming the mass hasn't changed, then you must have tripled the force. That's the only way that A could get 3 times bigger. Newton's third law is actually a little bit different from the first two. So the first two are saying if we have a net force, an object experiences an acceleration. If we don't have any, obviously there'll be no acceleration. So Newton's first law is almost a special case within Newton's second law. But Newton's third law is a little bit different. Newton's third law, we need to think about pairs of forces. So as an example here, you've got a hammer and it's hammering in a nail. The hammer initially is moving downwards, the nail is not moving. As the hammer collides with the nail accelerates downwards, but the hammer decelerates upwards. So let's think about the nail first. The nail is accelerating downwards. That means the hammer must be applying a force to the nail. That's the whole point of a hammer, is to apply a force to a nail. So if the hammer is applying a force to the nail, that force is what causes the nail to accelerate downwards. Great, everything makes perfect sense. The velocity of the nail changed from nothing to something because of a net force. Cool, easy enough. But what about the hammer? The hammer has gone from velocity downwards to no velocity downwards. That means it's decelerated, which is still just a type of acceleration. But according to Newton's second law, that means we must have had a force on the hammer. The only way for the hammer velocity to change is for it to experience a force. That means that as the hammer is pushing down on the nail is pushing back on the hammer. So we have this pair of forces. We can't just have a one-way force. There's always a pair of forces. This brings us to another definition, and that is interaction. A clarification on the definition. We've already defined interaction. We have two objects, with some effect on each other. In this case, a hammer pushing on a nail, but it requires two forces. We have to have a pair of forces. The two separate objects each experience a force due to the other object. So some examples here. When you push on the floor, when you walk, that's how we walk. We push on the floor to move ourselves forwards. That means the floor is actually pushing back on you. If you just pushed on the floor and the floor didn't push back on you, then you wouldn't be able to move. There has to be a force on you to cause you to accelerate. If there's no force on you, you can't accelerate. So just you pushing on the floor does nothing, but the floor pushing back on you is what causes you to move. A rocket, they work by expanding gas and pushing them out the thrusters, where we'll talk about gases a bit in the next half of the course, second half of the course. But essentially, the rocket is pushing on the gas to push it out of its jets, its thrusters. The gas is pushing back on the rocket as it leaves, and that's what causes the rocket to accelerate upwards. And with gravity, the Earth is pulling an object to make it fall downwards. That's what gravity is. The Earth pulls on the object, but the object pulls back on Earth. The Earth is so big, the mass is so huge. Remember that F equals ma. If the mass is ridiculously big, the acceleration is ridiculously small. So the acceleration of Earth due to the object falling towards it is practically nothing, but the acceleration of the object is noticeable. But it is still there. There is still a force on the Earth from the object as well as one on the object from the Earth. So every interaction always has two forces, one on each object due to the other one. And this is the idea of Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Or you may have heard it worded as, to every action there is an equal and opposite reaction. So the magnitudes of the two forces are identical, but the directions are exactly opposite. There's a few things that we need to remember about Newton's third law. Newton's third law is a common point of trouble for students that aren't used to thinking about physics and thinking about these forces and these sorts of scenarios. One force is the action force, the other is the reaction force. This point I'm not too concerned about. It makes sense in some scenarios, but as you'll see, it doesn't always make sense. So this one you can almost forget, but it's useful to remember because sometimes people talk about action and reaction forces, and it just helps you understand that communication. But the other ones are important. You cannot have one force without the other in terms of these interactions. You cannot have an isolated single force. Think about trying to push on an object without the object pushing back on you. Try and lean against the wall so that you're pushing against the wall, but without the wall pushing back against you. Doesn't make any sense. You cannot have a one-way push. You always have two forces in any interaction. They are always equal in magnitude, opposite in direction. Opposite in direction hopefully makes perfect sense. If you're pushing against the box obviously is pushing you the opposite way. The equal in magnitude is just because it is the same interaction. It is the one event causing this force. And they always act on different forces. So these force pairs, if it's you pushing on a box, one force will be applied to the box from you, the other will be applied to you from the box. So they're always acting on different objects. We're going to talk about these a little bit more just to clarify some stuff. But first, that first point about action-reaction. What is the action and reaction force in the following examples? A book resting on a desk, a finger stretching an elastic band, and two balls moving towards each other at the instant they collide with each other. They are interacting. What are the action and reaction forces? So again, 3 little quick scenarios. Pause the video if you want to have a guess at what the action and reaction forces are, and then we'll discuss further on the next slide, which is now. Firstly, the book. The book exerts an action force on the desk. That's its weight force. It's being pulled down by Earth, so it's pushing on the desk because it's trying to get downwards. The desk is therefore reacting to that and pushing upwards on the book to stop it accelerating down through the desk. When you stretch a rubber band, you are exerting an action force onto the rubber band because you are causing the rubber band to expand. The rubber band exerts the reaction force back on the finger. But the example with the two balls colliding, we don't have any information about which ball was first, which one was initiated by a person deliberately or anything, whether any of that happened. All we know is that there's two identical balls moving towards each other and they collide. We do not have enough information to distinguish between action and reaction force. So you can see that in some scenarios, action and reaction don't actually make any sense. There are still two forces. They are still a force pair. Ball 1 will exert a force on ball 2 and ball 2 will exert a force back on ball 1. But there's no way for us to call them action, reaction that actually makes any sense. And this is another common problem, is the idea that action and reaction forces might cancel out because you've got two forces that are equal and opposite things just cancel, right? This is when you need to remember very carefully that the two forces apply to the two different objects. So they can't cancel out because your forces on different objects can't cancel. Right? If we've got the person pushing on the box and the box pushing on the person, in terms of the box itself, it's just got the force from the person, and the person, they've just got the force from the box. So you can't cancel those two forces because they're applying to different things. However, it does get more complicated because you remember that we defined our system as being whatever part or parts, plural, of the scenario that we're interested in. So a system can include multiple different objects which do have action-reaction forces, and even though they're applying to different parts of the system, if they're all within the system, they're not going to be a net external force for the purposes of our force analysis. So we'll talk about a bit about what I mean here with the idea of a man in a shopping cart. So what I'm going to try and do, hopefully this works, is share my whole screen with two different windows so that you can see my document camera and the slideshow. So let's have a go at this. So hopefully now we're seeing the slideshow still in a small window and the document camera. So what we're going to do is just talk about a man in a shopping cart. So the scenario is a man pushing a cart and they obviously have to be on a floor. So we've got a man pushing a cart, my awesome little shopping cart drawing. So there's our shopping cart, man's headless, there we go. There's our shopping cart and our man. And the point of defining our system that we made was that we can choose the different parts. I realize that looks more like a pram now, but anyway, we can choose the different parts. We could choose our system to just be the cart, just the cart. We could choose it to be just the man and not the cart, or we could choose it to be both the man and the cart. Or we could even choose it to be the man and the cart and the floor that they're on. We could choose any of those to be our system. That last one is not a very useful choice in most cases because if we're using the floor as part of our system, there's not a lot for us to really think about. But normally we'd choose either the man, the cart, or both the man and the cart. That'd be pretty common choices. But you could get even more fine-tuned and you could say, we're just going to look at the handle of the cart and the man's hands, or just the handle even and not the hands. So we've got all these different options. You can define the system however you choose to. Once you have defined the system, then you have to think about whether each force interaction, those pairs of forces, whether they are internal to your system or external to your system. So let's think about just the cart. If we have just the cart, right, here's our cart, We're doing a free body diagram, not an actual diagram sketch. There's our cart. It's always going to have a weight force because we're on Earth. It's going to have a normal force from the ground. And it's got a push force from the man, because the man is pushing the cart. That's fine. The push force from the man to the cart causes a reaction force from the cart to the man, but the man is not part of our system, so we can't include that reaction force. So there's no way it can cancel this because it's not part of our system. So in terms of just having the cart, we have the push force, the normal, and the weight force. The weight and normal forces, remember, they are not a force pair either in terms of Newton's third law, because the normal force is from the floor to the cart. So the reaction pair to that would be the force from the cart onto the floor. Meanwhile, the weight force is from the earth onto the cart. The reaction force would be onto the earth from the cart. I think I might have said that round the wrong way, but anyway, you know what I mean. So you've just got to keep in mind the pair of objects that are creating the force, and therefore which force applies to which object. I've already mentioned this, the reaction force is on the man, so it's not part of our system. Let's move, though, to thinking about the system being the man and the cart. So here's our man, here's our cart. I'm drawing two objects and I'm labeling them both because we've got two different objects in our system now. Each of these has a weight force, and each of them has an equal and opposite normal force to their respective weight force. That means that they're not going to accelerate up or down. They're not going to float off the floor or go into the floor. That's fine. We also have the man pushing on the floor. I already mentioned that when you walk, you do so by pushing against the floor. That's how you move forward. If you didn't push on the floor, you wouldn't be able to move forward. The best way to remember this is to think of someone trying to walk on an ice rink. You've all seen in movies or videos, or you may have even tried it yourself. When you try and walk on an ice rink, if you try and push against the floor, there's no friction, so there's no way for you to actually push. Your foot just slides backwards. You don't actually get to move. So the only way you can move forward is to effectively push on the floor through that friction, and then the floor pushes back on you according to Newton's second law. So the floor is reacting and pushing you forward, or pushing the man forward. So we'll call that F floor. In the slide I have called it floor reaction, but we'll just call it F floor because the reaction is not part of our system. The action force is not part of our system because it is from the man to the floor, and the floor is not part of our system, but the floor back to the man is part of our system. We can include that force. We then have the man pushing on the cart. So he pushes on the cart. We have F push action, push action. That is pushing the cart to the right in the same direction that the man is being pushed by the floor. The cart, though, pushes back on the man equal and opposite. So back on the man equal and opposite, the man is part of our system, so we do need to include this. So F push reaction is still part of our system, or is now part of our system. It wasn't before. So what you can see is that our system does include both of those force pairs. And because we're considering the system as a whole and we want to know the acceleration of the system, that force pair is no longer relevant, because they are both internal to the system. They can't cause an acceleration of our system overall. Remembering that the man and the cart are actually connected, right? They are connected together in our scenario by the man holding the cart. So that's the idea here, is that you've got to think about the force pair, about which object each force applies to, and then determine whether or not you can include both the forces if both the objects are in your system, in which case you then get to cancel out those forces. We don't need those forces. We still need to remember they're there for our analysis purposes, but in terms of figuring out the acceleration, the net force, those two forces are going to be exactly equal and opposite by definition, so we can cancel them out. Also, by definition, our normal force and our weight force, because of our given scenario of a flat surface, a flat floor with a man and a cart on it, they are going to be equal and opposite, so we can cancel those out. So the only force that isn't cancelled out is the force from the floor onto the man, the reaction force to the man walking. And that is going to be what causes the cart-man system to accelerate. again, this is just expanding on what I've just been talking about, just repeating effectively what I've been talking about. The man and cart forces do cancel out. The force from the floor to the man does not cancel out. So we'll go back just to the slideshow now that we've done that discussion. External forces, no matter what forces are involved within a system, you need an external force to have acceleration of the system. Right? The system as a whole needs an external force to accelerate it. In our previous example, it didn't matter the force that occurred between the man and the cart. It doesn't matter how strong the force is that the man pushes on the cart with, because the cart pushes directly back on the man and cart was our whole system. It gets more complicated if we start to talk about the idea that the man could push the cart and then let go of the cart. And then what would happen? We've now got one system of two objects that can move apart in space. It does get more complicated. We're not going to go into those sorts of scenarios for now, but there is the requirement in our discussion that we had that the man-cart system sort of stays as one piece. Do practice keeping track of force pairs. Right? It's very easy to get confused with force pairs. The fundamental bottom line is that they always have to apply to two different objects, and those two objects are the ones involved in the interaction. Another common example of ones that get confusing is something like a box being pushed on both sides by two different people. We've got one person pushing left, one person pushing right. They're pushing equal and opposite on the box. The fact that these forces are equal and opposite, people tend to think, oh, they're cancelling out, they must be a force pair. They're not a force pair because they are both on the same object. They're both on the box from two different people. That's the result of two different interactions. So the force left on the box and the force right on the box are two halves of two different force pairs. The force pairs would be the force on the box from one of the people and the force back on the person from the box. And then there's another pair with the box and the other person. Here are some examples, some simple scenarios for you to have a go at. Head over to the forum, just like we did when we talked about the frames of reference. I'll start up a forum post and you can have a go at discussing these force pairs. So try and come up with different force pairs. Don't write too many all at once, because we do want everyone to have a go at getting involved. Again, just like we did with the frames of reference, if you feel like one of these scenarios has been exhausted, feel free to add a new scenario and start thinking about that as well. Remember to go through the force pair sort of process of thinking the interaction involves which two objects, and then the forces are going to be on each object from the other one. So there can be a lot of different force pairs in any scenario. For example, the first one, the rubber band being attached to the slingshot, you stretch it back by pulling on the rubber band with your finger. If you start to include the person's entire hand and arm and body and the floor they're standing on and everything else, you're going to get ludicrous numbers of force pairs. There would be ridiculous quantities. We'd never be able to get through them all. So we'll try and isolate a little bit to just what's directly inside our system or relevant to our system. But by all means, do think a little bit further if you want and start to think about some of the other force pairs that are sort of in the greater scenario, not just right in or within or external to our system. So there are 4 different scenarios. That first one I've just mentioned. The second one, you push against the wall with your hand. The third one, a boxer punches a punching bag. And the fourth one, 2 puppies playing tug of war with a rope. So you've got 4 discussion points there, 4 scenarios to discuss. So do head over to the forum and have a go at those. So that is the 3 laws, and this part 4, I've called it part 4, but it is just a recap of all 3 laws. Law 1, an object at rest or in motion at a constant velocity remains at rest or in motion at a constant velocity unless acted upon by a net external force. Remember that net external force means a force outside our system. So it has to be an interaction involving some part of the system and something outside the system. If it didn't, if there was nothing outside the system, there's nothing to have that force pair with. It's Newton's second law. The acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. And finally, part 3, if object A exerts a force on object B, then object B exerts a force of equal magnitude in opposite direction back on object A. So those are Newton's 3 laws, and that's what I expect you to understand today. As I said, we'd sort of already met most of the ideas. We hadn't talked much about force pairs, so Newton's third law was a bit of new information. But especially Newton's first and second laws, we'd effectively covered the content of those during the previous lesson. Today was just sort of formalizing those. So that's it for this lesson. We did introduce a new concept of inertia, which for these kinds of linear motion was effectively equal to mass. It is mass, but when we do look at circular motion in a couple of lessons' time, you'll see why we've got this concept of inertia separate to the concept of mass. It'll make more sense. Then we had the Newton's laws, and the last point there is being very clear about defining our system so that we can define the forces involved in the system and whether they're internal, a force pair on two different parts of the system, in which case we can cancel them out, or a force pair between something in our system and something not in our system, in which case we can't cancel them out, and that is a force we have to then consider in terms of analysing the motion of the system. So that's the end of this lesson, end of Newton's laws. The next lesson is going to look at common forces. So we've been talking about weight, we've been talking about friction, we've been talking about normal force, but we haven't really stopped and defined them clearly and said how we calculate and work with them. So that's the point of the next lesson.